Yeah, let me go over once again some points regarding recurrence that we discussed with regard to maps and coarse grained maps, and then give an example using the symmetric tent map, which we have already studied in some detail, as an illustration of the general principles involved. Recall that we had a phase space whose total measure was 1, and in this phase space I defined cells, and let us say this is some cell, some particular cell C, and then we were looking at the statistics of the recurrence of a typical phase trajectory to this cell in coarse grained dynamics. And just to recall to you what results, the sort of results we had proved, we discovered that if mu of C is the invariant measure of this cell, we asked for the measure of that set of events where a typical trajectory starts in this cell at time 0 and then returns to this cell for the first time at time n, and we call that the recurrence distribution. Okay. This we found was given by a certain formula in terms of a quantity Wn, which was the measure of all those events where you started in the complement of cell C at 0 and you remained in this complement till time n minus 1 and then go into this cell. In terms of this quantity Wn tilde, we discovered that the probability, and now I will use the word probability itself, for a recurrence, namely to return to this cell for the first time, and let me call that f, return probability of return for the first time at time n to cell C, given that you started in C at time 0. This was what I denoted by R the last time, but this is a more expressive notation. It says you started in cell C at time 0 and you return to cell C at time n for the first time without having come there before, after a sojourn the rest of the time in between in the complement to the cell C. Okay. So we are looking at the statistics of things which do this, start here and end up back there at a specific time n. This is the random variable here is n, and we are trying to find the distribution in this n. This was given by 1 over the measure of the cell C multiplied by Wn minus 1 tilde minus twice Wn tilde plus Wn plus 1 tilde. This was the formula we derived on very general considerations, and there were just two assumptions made in this derivation. The first was that there exists an invariant measure, that the system has settled down to some stationary probability distribution denoted by mu here, and the second assumption was that the system is ergodic, namely if you started anywhere the system walked around everywhere in phase space and came back eventually to this point, and it does so repeatedly. It keeps repeating itself over and over again. The system is not periodic, that would be trivial kind of recurrence. It is ergodic, and therefore we speak not of recurrences back to exactly the same phase space point as the starting point, but to some neighborhood of it, to some cell in which this initial point is. Notice that this has the structure of a second derivative in time, it is a second difference in time, and this itself is like a stay probability, because you start in some place and you stay there without moving out of it into the cell C. So it is essentially telling you that, and this is typical, it is a general sort of result, that the first derivatives of stay probabilities would give you escape probabilities, and the second derivatives would give you return probabilities. So in order to start at C and return back to C, return to C, you have to first leave C and then you come back. So it's, pardon me, it's like the second derivative in time, isn't it? This is just the second difference. The first difference in time would be something like Wn tilde minus Wn minus 1 tilde, and the difference of the difference is like a second derivative in time. So it is a second finite difference of course. This can be formalized, but intuitively it is clear what is happening. You have a certain cell C and you would like to find the statistics of return to this cell for the first time. Well, you have to go out and you stay there for some time and then you come back, and this is like the sojourn outside this cell. So you start here, you escape, you stay out, and then you come back. And so it is not surprising that exit time distributions or escape time distributions are like the first difference of stay distributions, and return distributions or recurrence distributions are like the second derivative in time, like the rate of change of exit time distributions or escape time distributions. So this structure is not surprising post facto, after the, and by hindsight it is quite physically quite appealing. Okay. Now of course remember also that we had defined W tilde to be equal to 1, and W1 tilde was simply equal to, if I set n equal to 1 here, it is just the invariant measure of C tilde itself. So mu of C tilde, which is 1 minus mu of C. Okay. I would like to now apply this problem, apply this general formula to a specific problem, and the problem we look at is the tent map, a one dimensional map, asymmetric tent map, because I would like to play with this parameter A and make it as small or large as I please. So the example we are going to look at is the asymmetric tent map. For which we already discovered that a coarse grain dynamics into two cells, this is A, this is 0, this is 1 and 1 there, a coarse graining into two cells, namely a left cell from 0 to A and a right cell from A to 1. This led to a transition matrix W, which was the probability that I start and the left cell, so this is L, that is R, and let us complete the diagram by writing an L here and an R there as well. So I start here and then I move to, I remain in L at 1. The other probability was L1 R0 P of R1 L0 and P of R1 R0. This is what I call my transition matrix W, and this was easily worked out to be equal to A and an A here, a 1 minus A and a 1 minus A. Okay. And my claim was that this is a Markov partition, in the sense that this probability that I am in either cell L or R, let me just denote these by I, J and so on. So I am in the cell J at time n, given that I start at cell I at 0, so let us put that 0 explicitly here, this quantity here. If it is a Markov partition, then you are guaranteed that this is equal to the Jith element of the nth power of the one step transition probability. This is a one step, in one time step, these are the probabilities of jumps, and if I take this matrix, raise it to its nth power and then compute the matrix elements, corresponding matrix elements, that should give you the nth step transition probability. Of course you can independently compute this conditional probability by just writing this out as a joint probability and then dividing by the absolute probability of starting at cell in cell I at time 0, and that will involve a delta function which involves the nth iterate of this map, asymmetric tent map. So it is a non-trivial problem to compute this nth iterate and then find out what this probability is, but I leave it to you to verify, and this is not difficult to do here, that this probability is indeed given by nothing but the corresponding matrix element of the nth power of this matrix, which proves that it is a Markov partition, and this is a consequence of the Markov property. Once you have this, we can now start computing what these probabilities are. That is very straightforward here, and what happens in this case, and we can in fact compute what this number is, okay. Because I just have two cells now, so C is, let us say, L and C tilde is R, just a Markov partition into two cells, and we can very easily compute what these probabilities are. What is this sojourn probability, for instance? What is the most interesting property of W, as I have written there? What are the eigenvalues of W? Yeah, the sum of the, as you can see, the sum of each column is equal to unity. What does that tell you?
The left eigenvector is,
yeah, that there is a uniform left eigenvector which is 1 1 and the eigenvalue is 1. And what is the other eigenvalue of this matrix? What is the determinant of this matrix? It is 0. So what is the other eigenvalue? 0 has to be the other eigenvalue. There are just two eigenvalues here. Therefore, it is immediately clear that for this matrix, at any rate, we have an extremely simple property, which is W squared equal to, what is W squared equal to if I square this matrix?
A,
1 and 0 are the eigenvalues, so the characteristic function, right, 1 and 0 are the eigenvalues of this matrix. So it is clear if lambda is an eigenvalue, this must be true. It is a 2 by 2 matrix, so this is the characteristic polynomial of this matrix. So it immediately implies that W squared minus W is 0, or this must be equal to that. Yeah, therefore it implies that all powers of this matrix is idempotent, all its powers are itself independent of A. Whatever be A, the matrix on raising it to any power gives the same matrix for all n. Of course, that at once tells you that the probability of being in L at time n, starting at L at time 0, is just the nth power, is just the 1 1 element of this raised to the n, which is the same thing as that. So this is equal to A, etc. So it is extremely simple in this case, and we can compute these numbers. What is W and tilde then? You can write this in terms of these probabilities and work it out, etc. So, but you can see this almost intuitively. A, 0 to A is L, and this guy is R, and this is our cell C, let us say. So this is the C and this is C tilde. Just for illustration I take C to be the left cell and C tilde to be the right, and then what is W and tilde going to work out to be in this problem? This corresponds, mind you, to the complement, so you have to be in R, and it is a stay probability in R. It is 1 minus A to a certain power, so this thing is equal to 1 minus A to the power n. So you are going to start at 0 and up to n minus 1 you are going to stay there, and it is just this. So what is the second difference? This thing in this problem, first of all, 1 over mu of C, that is just A, because the uniform, the invariant measure, invariant density is uniform, so the measure of the cell on the left is just A, the length of that interval, multiplied by 1 minus A to the power n minus 1 minus twice 1 minus A to the power n plus 1 minus A to the power n plus 1, right, and that gives you is there something I have left out? yeah, that is fine. Yeah. So this is equal to 1 minus a to the power n minus 1 divided by a and multiplied by 1 minus a the whole squared, right. Times that. So it is an extremely simple formula and it tells you something interesting. So it says the probability of return to this cell C at time n for the first time starting at cell C at 0, the recurrence probability is given by this geometric factor, it is a times 1 minus a to the power n minus 1. Similarly, we can ask for recurrence to the right, so let us do that. So let us write this f left n left 0 is equal to a times 1 minus a to the n minus 1, and similarly f r n r 0 equal to, well this is not hard to guess what this is going to be. Yeah, a and 1 minus a are just interchange between left and right, so this is equal to 1 minus a times a to the power n minus 1. And now let us check normalization. Because the system is ergodic, we have to be sure that there is recurrence that is going to happen. So if I sum this over n, I better get 1, and indeed I do. As you can see, if I sum from 1 to infinity, yeah.
Just that this seems counterintuitive to me because
Why?
the density is the invariant density is 1, right?
The invariant density is 1, yes.
It looks like the chances of it coming back to the same cells are diminishing over time.
No, this is not a question of, no that is not true. The chance of it coming back, the probability that is at L given this does not diminish, this is still equal to A, that is still equal to A. Now what does this correspond to? This is equal to the probability that if you start in L at 0, you come back to L for the first time at time n, for the first time, and of course you will keep coming back over and over again. So this probability summed over n must give you unity if the return is a sure event. We know it is a proper random variable, and indeed so, because if I sum this from n equal to 1 to infinity, this is just a geometric series, so it is a divided by 1 minus a, which is unity. So it is certainly normalized, this is certainly true, summation n equal to 1 to infinity f L n L 0 is equal to 1 as required. What is the mean time of return? What is the mean time that it takes to get back? N L say to the left, this is equal to a summation n equal to 1 to infinity n times f L n L 0. Now what does this work out to? So it is a summation n equal to 1 to infinity n times 1 minus a to the n minus 1. Now what is that equal to? It is just an arithmetical geometric series, so it is nx to the n minus 1, so it is just the derivative of x to the power n, right. So it is a times d over dx, if I have x to the n here, I differentiate it from 1 to infinity, the sum is x over 1 minus x, and I have to set x equal to 1 minus a. So what does this give you? If I differentiate this, I get 1 minus x so it is 1 minus x plus x over 1 minus x whole squared So that is 1 over 1 minus x whole squared, so that is 1 over a squared, which is equal to 1 over a, right. This is 1 over 1 minus x the whole squared, and I put x as 1 minus a. So I get 1 over a squared and I multiply by a, that is 1 over a. And indeed that is exactly what it should be, because we know that this must be equal to the measure 1 over the measure of L as required. The smaller a is, it is intuitively clear that the longer the mean time of return for the first time is going to be. So that was the reason for my choosing a here rather than a half, so that I can tune this, and you can see immediately that it takes longer and longer if a becomes smaller and smaller. Okay. The mean time of return to a specific point, which is a set of measure 0, will diverge, and that is exactly what is happening. And similarly n r equal to 1 over mu r, which is 1 over 1 minus a again. But then once you have this distribution, you can do more. You can find the variance of the time of return of recurrence of first return, and then all its statistics completely. What sort of distribution is this? This is some kind of geometric distribution. I could also write this as e to the power n minus 1 log 1 minus a. So it's some, and since log 1 minus a is a negative number, you can see that it is exponentially decaying in time, and this is very typical of these processes. Whenever you have a hyperbolic system, whenever you have no stable fixed points, nothing, I mean the map has got a slope greater than unity everywhere, this thing is said to be uniformly it is supposed to be hyperbolic, it is expanding everywhere at all points. Then it is characteristic of such systems that the distribution of recurrence is going to decay exponentially in time, and that is exactly what this does, because I could write this as e to the power minus n log 1 over 1 minus a, and it is an exponential decay in time. We can do more, we can go further and do this. We can even find limit laws, and let us see what I mean by that. You could ask, alright, if it comes back once, will it keep coming back? That is the first question, and if so, what is the statistics of such successive returns? And the other question you could ask is, I said this was a Markov partition, and I left it to you to verify that the probability that you start in cell I at time 0 and you return to it and you are back there in cell I at time n, or you are in some other cell j at time n, is just the jith matrix element of w to the n, the one step probability to the power n. What is the guarantee that this is Markov? Well, explicit verification, but do we have any general rules? Well, in this case, if the map is piecewise linear in one dimensional maps of this kind, if the map is piecewise linear as this is, and if your cells in phase space are such that the boundary points of these cells are either fixed points, everything is unstable of course, or are on periodic orbits, if they are on periodic orbits, or they are pre-images of periodic points, then the partition is guaranteed to be Markov. That is true in this case. Pardon me? Yeah. Where are the boundary points for this? Where are the end points for this partitioning? 0 is 1, a is 1, and 1 is 1, right? And the partition was simply L equal to 0 to a, and R was equal to 1 a to 1, something like this. Okay. Now 0 is already an unstable fixed point of this map, and where does the point the point A go? Where does this point go? If I start at this point, after one iteration I get to this and I am here, and in the next iteration I am at 0 again, which is an unstable fixed point. So the point A is a pre-image of the unstable fixed point at 0, and the statement is, if you take a an interval of this kind and you partition it, not necessarily into 2, if you partition it and you call this cell C1, C2, C3, C4 and C5, then if these points which are the endpoints of the cells, the boundaries between the cells, if they are either unstable periodic points or they are part of unstable periodic orbits or they are pre-images of such points, namely after a few iterations they fall into such points, then you can prove that the partition is a Markov partition. Of course you can refine this partition further, I can make this smaller and smaller, I could look at points which fall into A after one iteration and so on and so forth, and if I partition it further in this fashion, it is called refining the Markov partition, you are guaranteed that the partitioning stays Markov. So it is a useful piece of information to try, it is useful to try and partition a phase space into a Markov partition, because then you can use the machinery of Markov partition, of Markov chains, in order to analyze the dynamics, as we did here indirectly in some sense, because once you have a Markov process you have another property which I did not mention, a renewal property, which is the following. If I want to compute the probability of reaching some cell j, some state j of a Markov chain starting at some state I at 0, let us assume it is a stationary Markov chain, then this quantity is equal to, we can write a chain condition for it as follows. So you start at cell I at 0, move to a cell k for instance at time n prime for the first time, and then start in cell k and move in the remaining time. So if it is a stationary distribution, if it is stationary, then we do not need that, k n minus n prime to state j p, and this is equal to a summation over n prime equal to 1 to n. That is a renewal condition. It says you start here at 0, move to some other state k for the first time at time n prime, and then you start at that state k, and in the remaining time you end up at the state j. And then you sum over all the intermediate times here, and this is the first passage, first time you pass from I to j. So first passage time probability. So you should not have reached this k from I ever before till time n prime, and then in the remaining time you do this and you sum over all the n primes and you get this probability. Now the theory of Markov processes gives you a formula for this, because if you tell me the one step transition probability, I can find the n step transition probability by just raising that to some power n, right. Now how do I find these quantities? Those are precisely the quantities we want in recurrences, the first passage time, the first return probabilities. So I would like to have, in our case, what happens if I start at C and come back to C here. So I would like to put I and k equal to each other. What does this suggest to you? Is it possible for me to find this quantity, this set of quantities, given something for this set of quantities? What does it suggest to you? Think of n as time, and then this is a function of t prime and it is summed over t prime, and you have t minus t prime here. So what does it suggest? How would you solve this sort of equation? it is like an integral over t prime, right. So we have something which says, let me just use p here, you have p of t, it is going like integral dt prime up to t from 0, because you in discrete steps, if you make the steps small enough, times p of t minus t prime, and then this is some f of t prime. So what does this suggest? How do you solve for f of t prime in an equation? Pardon me? It is convolution, exactly. You take Laplace transforms. So that is the natural way to solve this problem. And therefore, if you took Laplace transforms here, in this case in discrete time, then you have a formula for this. And that is, in this case, it would lead exactly to the formula which we wrote down under general considerations here, the second difference term that we wrote down. So you have such a renewal equation. This is called a renewal equation. It is an example of a renewal equation for a Markov chain. It is a very convenient way of finding first passage time distributions, and that is exactly what we are interested in, the first return time distribution. So this is one more way of doing it. Instead of going through the general formalism, we could have done it this way as well in this case, because the partitioning was a Markov partition. Yeah.
The asymmetric tape map,
yeah.
we chanced upon it that it happens to be Markov chain by
Yeah.
coming across the distributions and finding them.
Yeah.
Is there some deeper principle which led you to believe that anything which is piecewise linear?
Yes, that is exactly the statement I made. There is a general way of proving that if you have a piecewise linear chaotic map, then if you Markov partition the interval, if you partition the interval such that the boundary points are either on periodic unstable periodic orbits or they are pre-images of such points, you are guaranteed that the partitioning is Markov. This can be established on general grounds. Okay. Once you establish that the partitioning is Markov, then you use the machinery of Markov chains to solve the problem. You do not have to go back to the dynamics, the actual map itself. All I have to do is to compute the transition probability in the transition matrix, the W for such a situation, and everything else is given in terms of W. Yeah.
Does this also mean that originally we said that finding the dynamics of a system is going to be non-trivial because you have to get into a difference equation?
Yes.
Can this be a route by which a generic solution can be found to any?
Not that you can solve it, but a great deal of information about the system is obtained once you manage to find a Markov partition, but there is no guarantee that for higher dimensional maps, other maps, non piecewise linear maps, etc., it is trivial to find such a partition, not true. So it goes one way, it is that if you have a Markov partition, then you are in good shape, this is what it implies, but how to find such a partition is not known in general. So it is not that we chanced upon the Markov partition here, it is just that I know that this map, the tent map, the symmetric or asymmetric, is a sort of paradigm of chaos in a certain sense. It is like the Bernoulli shift, it is a paradigm of chaos, and for such systems then we can see that a great deal of information can be obtained. Now most of the rigorous results that are proved in ergodic theory have to do with systems which are formally something called axiom A systems, namely at every point in the phase space, first of all there is an invariant measure, and at every point in phase space almost everywhere you have an expanding direction, you have something which is where you have, I should say in more technical terms, where the stable and unstable manifolds intersect transversally, they are not tangential to each other. So these are technicalities, mathematical technicalities, but what we are trying to do at a much lower level is simply look at some very simple low dimensional models, one dimensional models specifically, and use a little bit of the machinery of Markov chains to show that the actual dynamics can be removed, can be, you can cover it up, you can subsume it in the dynamics of a coarse grained Markov partition. So this is our modest aim here. Okay. We can, yeah.
Higher and higher iterates will give you more and more periodic points, right?
Absolutely, absolutely,
so
yeah.
I can say that at some point of time at a sufficiently
Yeah,
high
yeah.
iterate degree,
Yeah.
I can partition it into so many ways
Yes.
that I can calculate so many W's and finally land up at a very question.
Yes, let me rephrase what he is saying. He is saying if I refine this partition further and further, which I can by taking this map, taking the pre-images of this point and writing it in terms of more cells, then in principle I can go to a limit where I can perhaps even mimic the actual dynamics itself by doing this. Yes, yes, that is the eventual aim, that is of course the eventual aim in principle to do this, but it is not true in practice, it is not easily achievable in practice except in model systems of this kind. But if you can prove something is true in principle, then at least you have some idea that the results you get by studying this kind of analysis, by this kind of analysis, are reliable in some sense. So this is at that level, no more than that. Okay. In fact, let us answer this question directly. What happens if I have successive recurrences? What does it look like? Can I gather some general information from this? And let us look at that and ask, what is the probability? We have seen the probability that you come back for the first time at time n. We will ask the following question now. So we keep this in mind, that this is an exponential distribution, a geometric or exponential in n. Okay. So let us ask the following question, what is the probability that I return, if I start at L at time 0, that I return to L for the first time at some time n1, so let me call that n1 just for ease of notation. Let me say this is the first, this is the probability of return to L at time n1, and then after that the next return is at some time n2, and the return after that the first time is at n3 nr. So this is now asking for the probability of successive returns to L or recurrences to L at these instants of time. There are such recurrences, and I can ask what is the probability of this, how do I compute this? Well, this is not hard to do, because once we have this machinery that this thing is acting exactly like a stationary Markov chain, then it is not hard to show that this thing here is again of precisely the same kind. It is a times 1 minus a to the power nr minus r multiplied by a to the power r, I think. And it is not hard to see that this is equal to f at n1 times f, if I call this f of n for a moment, I call this f of n, f of n2 minus n1, f of nr minus nr minus 1. So it simply factors in this fashion. And what does that suggest to you? What does it suggest to you if I say that the probability of a recurrence in the sense we have defined at the instants n1, n2, n3 up to nr, the probability of r of these recurrences at these specific times is just the probability of a recurrence at time n1 multiplied by the probability of a recurrence in a time interval n2 minus n1, etc. up to here. What does that suggest to you about these successive recurrences? They are independent of each other, they are independent, statistically independent. That is the reason these probabilities simply factor in this fashion. So that is telling you how random this system is, in a sense, that this has completely factored out, and it is just a function of those time intervals, nothing more. So it is telling you that in these systems successive recurrences are statistically independent of each other. Not going to be always true, but in this instance it is so. Exactly, it is essentially due to the lack of memory in the Markov chain, in the Markov process, in this case the Markov chain. That is essentially what it is due to. You could ask, what is the probability given a certain amount of time n, what is the probability that I have r recurrences? Probability of r recurrences in a given time interval. What is that given? What is that equal to? What would that be? Well, we already have an expression there. So what would this be?
Find sum of all probabilities till nr is equal to.
Right. So you are given this now, and you are asking what is the probability of r recurrences appearing. So what would that be? This is already suggesting what the answer is going to be.
A power r, a 1 minus a.
Absolutely, it is a power r 1 minus a to the power n minus r, but you do not care in what sequence this is going to happen, right. So there is an n r, that is the binomial symbol, NCR if you prefer. It is the binomial distribution. And now we could ask, now final question, we could say suppose the time becomes very long, n tends to infinity, and let us say a becomes smaller and smaller. What do you think happens to this distribution?
Poisson.
It becomes a Poisson distribution. So in a limit in which n tends to infinity, a tends to 0, this distribution NCR, a to the power r 1 minus a to the n minus r, n becomes infinite, a goes to 0 such that the product of n times a is finite. This tends to the Poisson distribution. In R. So in fact let us make it such that limit NA equal to some number equal to lambda say. So what does this go to then in that case? What would this go to? Yeah, this goes to lambda to the r over r factorial e to the minus lambda, the Poisson. You shouldn't be surprised at this because the first one, the first recurrence as you can see is essentially a geometric distribution. It is the first term in that, and then successive recurrences would be Poisson distributed because they are independent. So this is the reason for saying that if you have an ergodic dynamical system in which there is chaos for example, and you are on the attractor or on the invariant set with some invariant measure, then if you take a sufficiently small cell in this system and ask what is the distribution of recurrences to this cell, that is Poisson distributed in this fashion. Okay. This is generic, this is typical behavior. It changes drastically once you have stickiness in the system, like we looked at intermittency. Then of course you can intuitively see this whole thing will go out of the window because the system would tend to stay in a cell where there is a marginal fixed point if it is just marginally unstable, and then the recurrence time distributions would be very different from this exponential behavior. Okay. In fact, it would start decaying like power laws, various power laws here. The limit distributions are not Poisson anymore. They could become Gaussians, they could become other stable distributions and so on. And this is a characteristic way in which you detect the existence of such intermittency or such stickiness in the dynamics. Because after all, everything depends finally on the behavior. If you looked at what we wrote for f of n, this went like this sequence Wn tilde minus twice n plus Wn plus 1 tilde, and there was a 1 over mu of c. We are looking at the long time behavior of this. In this simple case, it was an e to the minus n times something or the other, and we are asking what this does. Okay. So you can easily see, what would you say if Wn tilde went like 1 over n squared, for example? What would this go like for large n? It is like the second derivative, right. So it should go like 1 over n to the power 4 in that case. On the other hand, if this went like a 1 over n, then this goes like a 1 over n cubed and so on. So you immediately have the possibility of very slow decay, and then of course you are not guaranteed that you have a Markov chain or you have a Markov partition or anything like that. You have a general formula, and it could be as correlated as you like, which is what happens in the case of intermittency or in the case of systems which are not hyperbolic everywhere, which are the more typical cases, which in practice would be the typical cases. So the final comment one can make on this is that while we have these beautiful generic properties for classes of systems, dynamical systems, in practice, in real life, in a given dynamical system, you do not have this beautiful mathematical behavior. The system is not uniformly hyperbolic everywhere in general, and then you would have different kinds of recurrent statistics. You would have slow decays, you would have power laws and so on, which would give you some indication of what kind of sticky points are there in the phase space. So this is where I would like to end this little discussion of recurrent statistics per se and of this kind of coarse grained dynamics. We will look at some other examples subsequently, and now we move on to other topics. We talked a little bit about Markov chains, and we defined some of their properties of Markov chains. In particular, we looked at Markov processes in continuous time itself more than Markov chains, but then we reverted to Markov chains when we came to this coarse grained dynamics because it was in discrete time here. But essentially the essential property you need to remember, that is that it is one step memory, just the preceding step, nothing more than that. And then the statement I made was that the probability density that the variable is between x and x plus dx, say in a continuous case, state space case, starting at some x naught, this conditional probability for a stationary Markov process determines everything. It determines the process completely. If you take the limit of this as t tends to infinity, then this as t tends to infinity tends to a stationary probability distribution function p of x, which gives you the mean value, the mean square value, all the moments which are all independent of time. So in general, for example, the nth moment of this would not depend on time. This would be equal to dx x to the n p of x, but all 2 time and higher time probabilities, joint probabilities, are all given by this function in terms of this function here. Then the question is, what do you write for this equation? What kind of information or what kind of equation does this quantity satisfy? And we saw that this satisfies under suitable conditions. It satisfies a chain condition to start with, the Chapman-Kolmogorov equation, but in addition, under suitable conditions, we saw that this thing satisfied a master equation. Let us write this master equation down. So I said that delta over delta t p of x comma t. Let me for the moment drop this x naught, we will impose it as an initial condition, an arbitrary initial condition. So this thing here satisfies an equation of the form dx prime p of x prime t multiplied by a transition probability density per unit time, which was x prime minus p of x t prime x. This was the master equation we wrote down. Okay. Now I did not mention ways of solving this master equation. It is not trivial because it is an integral differential equation, as you can see, and then the initial condition on this p of x 0 could for instance be some delta of x minus x naught, that takes care of this conditional probability. Okay. Now how do we solve this kind of equation? It is not trivial, you have to know what this kernel is like, this transition density is like, but there is one case in which you can reduce this to a differential equation, which is in general easier to solve in some sense than difference equation, than an integral equation of this kind. Well, suppose you say w of x prime, which recall is the probability density per unit time, that if you start in the state x prime, you reach a value between x and x plus dx per unit. This is the transition probability density per unit time. This quantity here, what could this be a function of? In general it is a function of the starting state and the end state as well, but we could say, well, suppose this is a function of, I write this as some function of the starting state x prime and the jump x minus x prime. So let us write that as delta x, which is x minus x prime. It is a function of this and a function of that in general. Okay. Well, it is equivalent to saying it is also a function of x and x minus x prime, entirely equivalent. And now let us assume that as a function of this jump here, all the moments of this w exist. So let us assume that all these quantities integral d delta x to the power n w of x delta x. Suppose you assume that these moments exist. Let us give them some names, a n, and that of course be functions of x. Suppose for all non-negative integer n. Okay. Then under those conditions you can reduce this equation here. This equation here implies delta over delta t p of x comma t becomes a differential equation. So all we have to do is to substitute for that here in here, and then there is an integration which is doable, and you end up with this is equal to the following: a summation from n equal to 1 to infinity. Unfortunately it is again an infinite sum here, you have to pay that price, minus delta over delta x to the power n a n of x p of x comma t. You have to worry about convergence and so on, I am going to slur over those points, but you can show that this is equivalent to this differential equation. But it is an infinite order differential equation because you have the partial derivatives with respect to the state variable x of all orders in here. This expansion from this master equation, this is called the Cramer's expansion. You will see in a minute that you are actually familiar with this expansion, at least part of it. Now let us make a further assumption. These moments, what would you expect physically for any process in general grounds? You would say, well, this here is a function of the starting state, for example, and the jump, and the higher and higher moments of this could be expected to get smaller and smaller. Therefore you could say, suppose these ANs as n increases become smaller and smaller numerically, then I could perhaps truncate this equation at some stage. I could approximate this equation at some stage, maybe the first stage, second stage, and so on. It turns out that there is a systematic way to do this, and it turns out that the most common truncation is at the second stage. So you end up with an equation which reads delta over delta t p equal to minus delta over delta x a1p plus d2 over dx2 d2p. Okay. This is typical of what you get for such Markov processes, and this is called the Fokker-Planck equation or the forward Kolmogorov equation. There are several names for this equation. It is a first order in time and second order in the state variable partial differential equation. Okay. Now you are familiar with one example of such an equation. What is that? Which is that equation? By the way, this is called the drift term and that is called the diffusion term. And the ordinary diffusion equation that you write down for P is an example of such a situation. That equation, if you recall, was this. That corresponded to the case where you had no drift, here you had free diffusion of some kind, and this was a constant. So it came out and then you had this equation. So they begin to suspect that Brownian motion, which leads to this diffusion equation, is a Markov process. Indeed it is, it is called a Wiener process, and it is a special case of a more general situation. Okay. So processes where the master equation can be reduced from that level to this level, they are called in the mathematics literature, they are called diffusion processes as a generalization of this original diffusion equation. Okay. And you could ask, where do these can I write an equation for x itself? Yes, you can write what is called a stochastic differential equation for x, which is equivalent to this master equation for the corresponding probability density here. If I look at the motion of particles in this room at some constant temperature T, and I assume these are classical particles undergoing random collisions with each other, nothing else, then it turns out you can write such an equation for the probability distribution of the velocity of the particle, and that equation looks like this: delta over delta t p of vt for one component of the velocity, any Cartesian component, can be written as gamma times delta over delta v of v times p plus over m d2p over dv2. I will explain what gamma is in a minute, but this is Boltzmann's constant, this is the mass of a particle, and this is the absolute temperature, and this is what this distribution is for the probability density that the velocity of a particle is between v and v plus dv at a time t. You have to give me some initial condition, and the initial condition on this problem would be an arbitrary one. So you could start by saying that p of v0 equal to some delta of v minus v0, for example, and I can plot p versus p of vt, which is the solution to this equation here. It is a Markov process, it is a diffusion process, and it obeys a master equation of this kind here. Now what would you say is the distribution at t equal to 0? Well, it is some delta function at v0. And what is the distribution as time goes on? This gamma here is the friction constant in the system, it is related to the viscosity of the medium. Now what would you say happens as time goes on at t tending to infinity? what would you say would happen to this? Well, again remember that the probability distribution is Vt starting with some V naught, which is what we have written this for that initial condition. What do you expect will happen to this as t tends to infinity? I have this gas in equilibrium at some absolute temperature T, and now I look at some particle and suppose its velocity at t equal to 0 is V naught, and I let time evolve and I ask what is its probability density, fine. But what would you expect as t tends to infinity? It would certainly lose memory of V naught. What do you think will become? Pardon me? What do you think will happen to P of V comma T? It should go to the Maxwell distribution, it should go to the Maxwellian equilibrium distribution once again, right? And what would that be? P equilibrium of V. But what should this, what's this distribution? This is one Cartesian component of the velocity. So this is equal to e to the power minus mv squared over 2 kt, e to the minus the energy over kt. For a free particle the energy is half mv squared, and it should be normalized. So there is an m over 2 pi kt square root factor which normalizes this distribution. So I would expect that this distribution at t equal to 0 goes into this at t tends to infinity. So this is t equal to 0 and it should drift back and go into this, and let us check if that is true. That is easily done, okay, because that distribution at t goes to infinity is independent of time, and I can write this as a total derivative for the equilibrium distribution. So let us do that quickly. I expect 0 equal to this, and now let us convert this to a d over dv and make this a d2 over dv2, and this is P equilibrium, V times P equilibrium, and the gamma cancels out like this. And we could take out a d over dv and write it in this fashion. So if this is 0, it implies this thing is a constant. What can this constant be? Well, I know this P equilibrium must have finite moments, therefore as V tends to infinity it must vanish faster than any power of V or inverse power of V. So as V tends to infinity, plus or minus infinity, I want this to go to 0 and I want this to go to 0, so the constant is 0, because it must be 0 at V equal to infinity and independent of V, therefore the only constant you can have is 0. Well, that is a trivial equation to solve. It says dP equilibrium over dV so it says dP equilibrium over dV equal to minus mV over kT P equilibrium. What is the solution to that? This is the solution, that is the solution. So indeed this is happening, this is tailored to happen. So we have an example of such a Markov process, namely the molecules in this room. Their velocity represents a Markov process, a diffusion process over on top of it, and it is in continuous time. Okay. So that is the simplest physical example, direct physical example of a Markov process under suitable assumptions. We have made a large number of assumptions here. This is a specific model of randomness we have assumed, but it is a very satisfactory one.